All right, today we're going to talk about solving absolute value inequalities, which in many ways it's very similar to solving equations, except for one little tweak that we have to make, and that's what we're going to talk about to start the video. So, when we look at the absolute value is greater than 2, and we want to find all values of x that make this true. First off, it's different than equations because we're not just going to have two solutions. If this was an equal sign, this equation would result in two solutions. Well, with inequalities, we're going to have infinitely many solutions. So I'm going to use a number line to display what those solutions would look like. So we have to think, what does absolute value mean? So the absolute value of some number we're calling x is greater than 2. That means we're greater than 2 units from 0. So if I draw a number line here, to be greater than 2 units from 0, on the positive side of our number line, that means we're going to be at 2, but we have an open dot there because this is strictly greater than, so we're not including 2, and to the right. Okay? Then, on the negative side, well, if we're at negative 2, we can't go to the right from negative 2 because that's closer to 0. So we have to go to the left, so I'm going to shade to the left. And this shaded region represents all the possible x values that satisfy this inequality. So how can we write the solutions from this number line? Well, this is the same thing you do in middle school, all right? So this is saying that x, which is the same x as the one we started with, has to be less than negative 2. We're going to use the word or here because it can't be between them. So these are two separate intervals. Or x has to be greater than 2. And there's our solutions to that inequality. All right? So to check and see if these are right, remember, you can always pick a number that's less than negative 2 and plug it into the original. So let's pick negative 5. Negative 5 is less than negative 2. If I plugged in negative 5 into the absolute value, I'd have the absolute value of negative 5 is greater than 2. And ask yourself, is that correct? Well, yeah, it's correct. The absolute value of negative 5 is 5, and 5 is greater than 2. So that's good. All right, so we know that this one's correct, and we can do the same thing with this solution of x is greater than 2. All right, so what about the next one? Well, notice in this one we have the less than sign. So we have the absolute value of x is less than 2 units. So again, I'm going to draw a number line. And on this number line, I'll put 0 there, since we're relating to 0, units from 0. So if I'm going to be less than 2 units, but it's strictly less than, so open dot, I have to be closer than 2 to 0, so that I'm going to shade to the left. Okay, now I'm not going to shade too far because you'll see in a second what happens. Well, we can be at negative 2, because that's 2 units, not including it, because it's strictly less than. Okay, if we want to be less than 2 units, we have to shade to the right. So now in this case, our shading is in between 2 values. In this one, it's on the outside of those 2 values. On this one, it's the inside. So we can write this all as one inequality, similar to the way we would write domain or range. So we're going to have negative 2 has to be less than x, which has to be less than 2. Okay, and that's our answer, or one way to display our answer. A separate way would be to say x has to be greater than negative 2, and because this also has to be true, and x has to be less than 2. These two statements say the same thing. So you get to choose which notation you want to use. All right, now the next two. We have the absolute value of x plus 4 is greater than or equal to 1. So again, forget about the x plus 4 for a second. Put my finger there, so my finger is in the absolute value sign. If the absolute value, the distance from 0, is greater than 1, that means I either have to be to the right of 1 on a number line. So this isn't our solutions. This is just to help us visualize what this is saying. Okay? We have to be from 1 and greater than 1 to be more than 1 unit from 0. Or if we're at negative 1, and notice I'm using closed dots because of the equal to inequality, at negative 1 and to the left. All right? Well, we don't just have x underneath the absolute value. We have the quantity of x plus 4. So we're going to write that x plus 4 has to be greater than or equal to 1. That's for this side. Or x plus 4 has to be less than or equal negative 1. So notice, like equations, I still have two solutions, one positive, one negative, but I had to flip the sign on that second one. Okay, and that's because of the statement we're given and how absolute value works according to this number line. All right, so now we just solve this inequality. So we get x has to be greater than negative 3 because we subtract 4 from both sides. Or if we subtract 4, we get x is less than or equal to negative 5. So let's put these solutions on a number line. So I'm going to say negative 3 is there, negative 5 is there. Okay, so x has to be greater than or equal to negative 3, so that's a closed dot on 3, shaded to the right. And then a closed dot at 5, shaded to the left. So notice our intervals again are disjoint, meaning there's no overlap between them. All right, so that's why we use the statement or. So this is your solution. All right, so the next one, we have the absolute value of 4 is less than or equal to 1. So again, a little number line. If we're going to be less than 1 unit from 0, that means we have to be, our quantity inside the absolute value has to be between negative 1 and 1. So that is greater than negative 1, but less than 1. So our quantity is x plus 4. So we're going to have x plus 4 is less than 1. And the reason we use an and is because it's between these two values. This has to happen at the same time. It has to be less than or equal to 1 and at the same time greater than negative 1. And then we solve. So we subtract 4, subtract 4. So x has to be less than or equal to negative 3, and at the same time, x has to be greater than or equal to negative 5. So if we put that on a number line, here's 0, negative 3, negative 5, closed dots, because the sign we started with was an equal to inequality, and we shade in between them. All right, you try these on your own, and in a second I'll put up the answers to see if you're right. All right, so the solutions you should have got are x is greater than 3 or x is less than negative 5. And for the next one, you should have got x is less than 0 and x is greater than negative 8. And here's what the graphs look like to represent those solutions. All right, so now we're going to solve these inequalities graphically, before we start algebraically dealing with some more complicated inequalities, let's see what's going on a graph so we can get a picture of what's going on when we do the algebra. So the idea here is to take the left side of the inequality, this absolute value of x plus 3 plus 1, and graph that, and on the same set of axes, graph y equals 4, and then see where they intersect. All right, so that's our plan. That's what we're going to do. So I'm going to consider the graph of y equals the absolute value of x plus 3 plus 1. Okay, so our vertex, this is in vertex form. So our vertex is -3, 1. So I can put that on the graph. My a value is positive, so I know it's going to be opening upwards. So I need another point, and I'm going to try and get the y-intercept. So hopefully you recall from our sketching lesson, to find the y-intercept, you replace 0 for x, since if you're on the y-axis, the x value is always 0. So I'm going to have y equals the absolute value of 0 plus 3 plus 1. So that is the absolute value of 3 plus 1. The absolute value of 3 is just 3. And 3 plus 1 is 4. So my y-intercept is 0, 4. So I'll plot that point. Now, if I had one more point, I can draw the graph because I have what this side of the graph will look like. It's just going to be a straight line through those 2 points. So how do I find one more point? Well, to answer that, we're going to use symmetry. All right? So there's an imaginary line that splits every absolute value function in half, and it goes through the vertex. Sometimes it's called the axis of symmetry. Okay, so this point is 1, 2, 3 units away from the axis of symmetry. So to get the next point, I'm going to count 3 units to the other side of the axis of symmetry. 1, 2, 3. So my next point is going to be there. Now all I have to do is play connect the dots. And I've sketched this function. Now we need to see where y equals 4 intersects this graph. So the line y equals 4 is a horizontal line where y is 4. So I'll label here. So that's y equals 4. This is y equals absolute value of x plus 3, and then plus 1. So what this equation is saying is it wants to know where this function is greater than this function. Well, and it wants to know x values, okay, because we're searching for x values. So what we look at is we look at the x values where the 2 graphs intersect. So this graph intersects at a y value of 4 and x value of 0. Now, you have to be careful. Look at the inequality we used at the beginning of this inequality. It's a strictly greater than. So that means that all x values that are greater than 0, because that's where they intersect, all of these x values on this graph are going to be bigger than 4. So all I'm doing is I'm shading, just like I did previously with the equations, or with the inequalities up here. I'm doing the same thing, I'm just doing it on the x-axis. Okay? Now what about on the other side? Well, the other side, the graph intersects at -6. So all x values to the left of -6 provide y values that are greater than 4. So now all I have to do is write what's on the x-axis, and those are my solutions to this inequality. So we have x is less than -6, or x is greater than 0. And that's how you solve algebraically. All right, example 2, it's the same thing. So I'm going to sketch the graph of y equals the absolute value of x plus 1 minus 4. Then I'm going to sketch the line y equals -2, and I want values that are less than y equals -2. So let's see what that looks like. So again, this is in vertex form, so the vertex is -1, -4. Okay, again, I'm going to use the y-intercept. So I'm plugging in 0 for x, then evaluating, and I get -3. So I'll put the vertex along with the y-intercept. Again, your a value is positive, so I know it's going to open up. And I'm going to use symmetry to find the second point. Okay, so there's the graph. This line's a little off, but I think it's good enough for at -2. All right, and then I'll sketch the line y equals -2. Okay, so I want to be less than -2, so that's all of this part on the graph, all of those x values. So let's see what that corresponds to on the x-axis. So it starts at -3, and then to the right, this part of the graph is to the right of -3. And then on the right side, it stops at an x value of 1, because at 1, the absolute value function becomes greater than -2. All right, and we're using closed dots because this is less than or equal to. So our x values are going to be everywhere in between -3 and 1, so we just need to write that. So x has to be greater than or equal to -3, and at the same time, less than or equal to 1. Okay, do you have to write it this way? No, you could write it this way as well. Both of those are the same thing.